Hello everyone, I am Aswani, Assistant Professor, Department of CSE AIML, MLR Institute of Technology. Today we will discuss propositional logic. So, what is a propositional logic? What is how we will explain the formula, how to derive the satisfiability, unsatisfiability, and how to prove that formula. We'll discuss all those things. Let's see the overview of the presentation. In today's session, we will see the propositional logic introduction and what are the other methods rather than this propositional logic. We will see natural deduction system, axiomatic systems, semantic tableau, and resolution refutation methods. Let's see the propositional logic introduction. So the propositional logic or prop logic deals with the validity, satisfiability, and unsatisfiability of a formula, and the derivation of a new formula using the equivalence laws. We know already there are some of the equivalence laws are there, De Morgan's law, distributive law. Using those, we'll derive the validity and satisfiability and unsatisfiability of a formula. So each row of the truth table, for example, A, true, false, negation of A, false, true. So in this, each row of a given formula alpha is called as an interpretation. This first row is called as interpretation. The second row is also called as interpretation, under which the value of formula may be true or false. Okay. A formula alpha is said to be a tautology if and only if the value of alpha is true for all the interpretations. So here, for example, if you derived some alpha, in all the interpretations we derived the true, then it is said to be a tautology. So now the validity, satisfiability, unsatisfiability of a formula is given as a formula alpha is said to be valid if and only if a tautology. Means if the alpha interpreted as all interpretations are true, then it is said to be a tautology. When it is said to be a tautology, then it is said to be a valid. A formula alpha is said to be satisfiable if there exists at least one interpretation for which alpha is true. For example, alpha is true, false, false, false. Then this is said to be satisfiable. A formula alpha is said to be unsatisfiable if the value of alpha is false under all interpretations, then it is said to be unsatisfiable. When it is satisfiable, when even one of the interpretation of alpha is said to be true, then it is called as satisfiable. If all the interpretations of alpha is false, then it is said to be unsatisfiable. When it is valid, when alpha is said to be in all the interpretations are true, then only it is said to be valid. Okay, let's see one example. Show that the following is a valid argument. So if it is humid, then it will rain, and since it is humid, today it will rain. First we will symbolize each part of English sentence. A equal to it is humid, B equal to it will rain. Now the formula corresponding to the given sentence is this: if it is humid, then it will rain. Then we will use the implication A implies B. So if it is a humid, then only it will rain. And since it is humid, this one is the fact. So it is a humid today, then it will rain. So and A implies B and it is humid, that is fact. A implies B. So here we have used modus ponens rule, which means if A implies B and A is true, then automatically the B is also true. As a consequent, B is also true. That is said to be by modus ponens rule. A implies B and A is true, then the B is also true as a consequent. So let's check the truth table for this. A implies B and A implies B as a true or false. Let's check what is alpha, whether it is a valid or satisfiable, unsatisfiable. So we know the truth table. A, B, A implies B. If both are true, then it is true. If both are false, then it is if true and false, then only it is false. In remaining all the cases, it is true. Next, this one is taken as a X and A. So here it will take T, true. Remaining all cases, false. Then Y implies B. The entire case and implies B. In this case, when it is true and false, then only it is false. Otherwise, in all the cases, it is true. Let's check. Y implies B. True. There is no true and false here. So, remaining all are true. So, this one is A implies B and A is true. Automatically, the consequent B is also true. So, it is said to be valid. Why it is said to be valid? Because the alpha interprets all the cases. Each row interpretation is true. Then it is said to be tautology. When it is a tautology, then it is a valid formula. Okay, let's see. In truth table approach, for example, there are n atoms are there. Then how many interpretations are there to find out something? Here it is 2 to the power of n entries we need to compute. So here if you see this formula, then we need to find out the result. We need to take the 32 rows to complete the truth values. So if it is a large number, then it automatically increases the truth table also. So this is one of the drawback here. To overcome this, we are having other methods also to find out the satisfiability, unsatisfiability and validity. Here, natural deduction system, axiomatic system and semantic tableau method, resolution refutation method. Let's see one by one how it will prove the theorems or how to validate the given formula. The first one, natural deduction system. In natural deduction system, the name itself, it will take the natural reasoning. The system is based on a set of deductive inference rules. So it contains the 10 deductive inference rules, which means we are having 5 connectivities: negation and or, implies and equivalence. So for each connectivity, we have 2 inference rules, that are 2 deductive inference rules, that is, one is for introducing, another one is eliminating. So in this natural deduction system, all about a hypothesis. So to derive some formula, to get a conclusion, we need to assume something. When we need to introduce some connectivity, when we need to eliminate some connectivity, so that we can draw the conclusion. So here, these are the 10 deductive inference rules which are used to draw the conclusions. And one modus ponens rule, already we have seen in the previous example. If P and P implies Q is true, P implies Q and P is true, then we can infer that Q will be true. So if it is true, then automatically Q also true. That is said to be modus ponens rule. So here, if you observe, introducing and, eliminating and, introducing or, eliminating or, in such a way we are having the 5 connectivities, introducing and eliminating symbols. All we need to assume such a way that we can draw the conclusions. Okay, let's see one of the example here. Prove that A and B or C is deduced from A and B. So we need to infer from A and B, infer A and B or C, B and C. So here the theorem is from A and B, infer A and B or C. So the hypothesis is given as A and B. We have written, these are the line numbers 1, 2, 3. This one need to be proved, and at last we have proved by using some assumptions or hypothesis. So the hypothesis is given as A and B. So here we need to get A and B or C. We need to assume the value such a way that we can draw the conclusions as that A and B are C. So here from this we have to eliminate this one. We need to take the values individually. So eliminate, and so here after eliminating A, B from the 1, So here we have taken line number as 1. So eliminate and 1. The row number is 1. So we have taken the value as 1 and we have eliminated. After eliminating, the values are A and B. Next, we need to get this value. To get this value, we need to add R and C to the 3, row number 3. For that, introduce R symbol to the which row 3. So we have drawn like that, B, R, C. Next, we need to introduce again and with the 2 and 4. So introduce and 2 comma 4. So that will reach the conclusion. That will be proved. So in natural deduction system, all about assumptions, hypothesis, what we need to introduce, what we need to eliminate. Already we are having all the deductive inference rules. By using those rules, we need to get the conclusion. Let's see the next example. A implies B and B implies C implies A implies C. So here assume that A implies B and B implies C assumption. In the next one, we have assumed A, and after that, what is the given value we have taken and eliminate and symbol from the 1. So we have eliminated. After eliminating, A implies B and A implies C. Okay, so the next one, eliminating implies symbol 2 comma 5. So when we eliminate, we have B. Next, B implies C. When eliminate from 4, we have B implies C. Next, in the 9th, we need to have C. So we need to eliminate implies symbol so that we'll get the C. At last 10, we have taken the value from here. Okay, A implies C. Introduction from 2 to 9. Then we have A implies C. At last, we derived the values from 1 to 10. A implies B and B implies C and A implies C. So I said already, to draw the conclusion, to prove some formula, we need to assume what we need to eliminate, what we need to introduce. That's it. Okay, the next approach is axiomatic systems. So in this axiomatic system, we consist of set of 3 axioms and 1 rule called as modus ponens rule. We have already seen that modus ponens rule. So in this system, we'll use only 2 logical operators, that is negation and implies. So if it is using equivalence or and, then we need to convert these symbols with the negation and implies. So that system says that it is an axiomatic system. The axiomatic system consists of only these 2 values. If the formula contains these values also, by using the equivalence laws, we need to convert those connectivities with this negation and implies. Okay, it should not noted that other logical operators such as and, or, equivalence can be easily expressed in the term of negation and implies using the equivalence laws. Let's see some examples here. A and B. When we perform double negation, then it will be negation A or negation B. Then it can be easily expressed as negation of A implies negation of B. So we can prove this using the truth tables also. This truth table is an easy approach to do, but if the more atoms, then more interpretations it needs. It will be increased as the tabular format also. But here it is a simple one. We can easily identify this also. Okay. In similar way, A or B means negation of A implies B. A equivalence B is a negation of B implies A. Applying all this, we can get at last this one. Okay. Let's see what are the 3 axioms and 1 modus ponens rule. The first axiom one is alpha implies beta implies alpha. Here alpha, beta, gamma are well-formed formula. Next, axiom 2 is alpha implies beta implies gamma. This one is a distributive law. Alpha implies beta, alpha implies gamma. Next, axiom 3 is negation of alpha implies negation of beta implies gamma. So the modus ponens rule is alpha implies beta and alpha consequent beta is true. So here given that alpha implies beta and alpha are hypothesis assumed to be true, then beta is also true. Let's see one example of axiomatic system. Establish that A implies C is a deductive consequence of A implies B, B implies C. That means A implies B, comma, B implies C is equivalent to A implies C. We need to prove that A implies B, B implies C is A implies C. So what is a hypothesis 1 is A implies B, hypothesis 2 is B implies C. So the instance of axiom 1, the axiom 1 says that alpha implies beta implies alpha. So here we have taken alpha is B implies C, then this one is beta. Then alpha implies beta implies alpha. So B implies C implies A, here A is beta, alpha implies beta implies alpha. B implies C implies A implies B implies C. Okay. Next, the modus ponens rule 2, 3 is, we have taken 2 and 3 here. So here alpha implies beta, alpha implies beta and alpha, then beta is true. So here we have taken this one is alpha, this one is beta. So from this 2, 3 we derived that A implies B implies C is true. Then instance of axiom 2, A implies B implies C, here this one we have used the second axiom 2. Then A implies B implies A implies C, the second axiom. Next, again applying modus ponens rule. So A implies B implies A implies C. This one is alpha and this one is beta. Then we will get the A implies B implies A implies C. From modus ponens rule 1 and 6, we derived that A implies C. So out of these rules, whenever we have the formula, which axiom is applied, which rule is applied, to get the conclusion, we need to derive the rule. We need to apply the rules so that we can derive the proof. We can conclude that we have proved that formula. Okay, first we have taken these values and we shown that this one is equivalent to A implies B, comma, B implies C by applying this axiom 1, axiom 2 and modus ponens rules, and we proved that A implies C. Okay. So in this session we have seen that propositional logic. So in this propositional logic we know that there are 5 connectivities: negation, and, are, implies and equivalence. So here when we apply the logic to the propositional statement, then it is called as a propositional logic. We know the truth tables here. In this we seen that propositional calculus, that is nothing but truth tables of all these things, all these 5 connectivities. After this we have seen the other methods of the rather than this propositional logic. By using this propositional logic, we can find out whether it is a valid, satisfiable or inconsistency by using truth tables. But here the problem is if the number of atoms are increases, then automatically the interpretations also increases. That is one of the drawback in this propositional logic. To avoid that thing, then we have other methods. In this session, we have discussed a natural deduction system. So we have 10 deductive rules using these 5 connectivities that are introducing and eliminating, all about the hypothesis to derive the conclusions. And the next one is, we have seen axiomatic system. In this axiomatic system, we have 3 axioms and 1 modus ponens rule. And we have seen one example also. In the next session, we will see the resolution refutation method and semantic tableau method. Thank you.